In this video, we'll be looking into the important concepts of fourth module, that is levels of testing and integration testing of software testing subject. So starting from the first chapter, that is levels of testing, our first topic is waterfall model or waterfall life cycle. So waterfall life cycle is also called as a traditional view of testing or a classic method of testing. So we know about waterfall model, that is firstly we have the requirement specification. Once the requirements are obtained, we'll perform the preliminary designing, and once the preliminary design is done, we'll further move with the detailed design part. Once the detailed design is obtained, we come to the coding part. So in coding part, we extensively code for each and every functionality which we have decided upon. Then we move to the unit testing. So we'll be testing each of the functionalities one by one and make sure that there are no errors in it. Then we go to the integration testing, where we combine all these units, where we combine all these functionalities and test further. So after testing, once unit testing is done, integration testing is done. After extensively coding, we look into the testing part. So firstly, we have is the unit testing, where we test each of the functionality. Each of the unit is tested separately, and we make sure that there are no errors in that unit. After that, we move further in integration testing, where several units are combined for testing. So after combining several units, we perform integration testing. Next, we move on to the system testing, where the entire program and the system compatibility is checked. Okay, so we check the entire program with the system with different scenarios. So this is what we have studied about waterfall model or waterfall life cycle. So we know that this is one of the classic models. So this model is associated with top-down development and design by fundamental decomposition. But speaking of bottom-up integration, that is units at higher levels are replaced by drivers that emulate the procedure calls. So here, instead of proceeding from top to bottom, we go from bottom to up. Okay, so that's what bottom-up integration says. That is, units at higher levels are replaced by drivers. So these units, no, instead of making use of units, we make use of drivers. So combining these drivers with the procedure calls, we perform the bottom-up testing, bottom-up integration. We'll look into this further. So firstly, we have our partial functional decomposition of SATM system. So firstly, we have the ATM system. From ATM system, we have three options. That is, one will be the terminal input output. So terminal input output would display all the necessary information to the user. Then we have managing the sessions. So sessions are managed when you put the card. No, that's when sessions start initially. That is, first you put a card and then you enter the pin and then you select the transaction. Once managing the session is done, now you'll look into the conduction of that transaction. That is, depending on what transaction you have chosen, you will be conducting the transaction here further. So this is a partial functional decomposition of SATM, because in terminal input output also, in selecting the transaction also, there are further levels, right? We can decompose this further. We'll look into it in the upcoming further. So yeah, this is an important question. For sure, it will be asked for 10 marks, guys. So from levels of testing, this will be asked. So make sure you study this properly. So firstly, we have alternative life cycle. So alternative life cycle emerged because of the weakness of waterfall development. That is, a waterfall method was not able to cater properly. So there was no feedback in it. It was very long separation between the requirements and the complete system, and over reliance on the whole the program functionality. But then in the middle, during the testing part, if the user gave any changes, the team was not able to incorporate it using the waterfall method, right? So these were certain disadvantages of waterfall method. So to overcome this, we came up with the alternative life cycle models. So the first one we have is waterfall spin-off. Waterfall spin-off is there are three mainline derivatives for this model. One is the incremental development. Incremental development means we are getting the requirements from the user and then programming it, and after programming it, we are building upon it, we increment it in several sequences. That is, series of builds are produced. Okay, so firstly we took an input, we developed we developed the code, we did all sorts of testing, unit testing, regression testing, integration testing, and progression testing. After that, we take again this was for one functionality, right? Next, we'll move on to the next functionality. Again, we'll check the functionality by taking the requirement specifications and then performing the preliminary design and then series of build. That was about incremental design. Speaking of evolutionary design, here it is same as incremental design, but then we start with the we build first defined model here, defined build is used here. Okay, initially the sequence is defined, after that we look upon into the series of builds. Again, evolutionary way it is incremented. Then we have spiral development. Spiral development is combo of rapid prototyping and evolutionary development. So here waterfall spin-offs have easier synthesis and customer feedback, and we mitigate some deficiencies of waterfall method. That is, to overcome the deficiencies of waterfall method, we look into the waterfall spin-off. So firstly we have is the life cycle with a build sequence. So as you can see, detailed design is considered. After that I do the coding part, then I do the unit testing, integration testing, regression testing and progression testing. So the goal of regression testing is to make sure that the things work properly in the previous build. It will still work same way in the new added code. Coming to progression testing, we assume that the regression testing was successful and that new functionality can be tested further. That is what progression testing speaks of. So this was about regression testing, progression testing. Rest all we know the definitions, right? So here, based on the later builds are identified, usually in the response to the priorities set by the user. So this system revolves to meet the changing needs of the user. So you build one particular functionality, gave it to the user, again took an input from the user, specification from the user, and again get back to building it again. So in life cycle with a build sequence, the software is developed in sequence of builds where each build adds a particular functionality to the overall program. So here it also allows us to perform testing at each level. That is, once we start the detailed design part, then we code, and then we perform the unit testing, integration testing, regression testing and progression testing. Understanding the definitions of regression testing and progression testing, the main goal of regression testing is that whatever the functionality or the build which we have selected worked perfectly in the previous build, and we'll check if it will work the same in the newly added code. And coming to progression testing assumes that regression testing was successful and the new functionality can be tested further. So with this belief, we move further and look into the series of build part. So here we can easily adjust the development plans as each build will reveal more about the project's details. Okay, so once we started with a particular functionality, we did all these steps, and then it was given back to the user. User gave some feedback, required specifications, and then with those specifications we designed the preliminary description, and from that preliminary design, and from that we came to the series of build. So it happens this way, and on the other hand also we are getting feedback from the user. So we are providing a opportunity for the user to put forth his or her opinions or thoughts about the each and every build which we have designed. Moving on further, we have rapid prototyping life cycle. Rapid prototyping life cycle ali, first we create a prototype. Prototype can be a working model or a working model only of a software which is developed to make sure that the user understands what we are working upon. So series of builds. So series of builds, in this we have firstly the preliminary design, and a series of prototypes. In that we have preliminary design, detailed design, coding, unit testing, integration testing and system testing. But before getting into the preliminary design, we first build the prototypes. Series of prototypes andre we build several prototypes by defining the project objectives, building the prototype, and then taking the customer feedback. So here user interacts with the prototype, providing feedback on how it is. Then this prototype is iteratively refined on basis of what user says, and then we come up with a final prototype. Having that final prototype as a landmark, as a goal, we then look into the further parts, that is preliminary design, detailed design, and then the coding part and all. So here our development time is reduced, because as we keep on building prototypes, we keep on developing the features. Once we develop all the features and and the customer is satisfied with what we have come up, he'll be like, okay, you can start with the further process, and then we get into this part. So rapid prototyping is it is efficient, it saves time, and it is risk reduction also, because in the later stages, if there is any risk, we cannot change it, we cannot rectify it. We have to get back to the initial part again. So this was about rapid prototyping life cycle. Moving on further, we have executable specification. Executable specification andre we make use of formal specifications here. That is, executable, we make use of a formal executable model of software to define the requirements and system behavior. So executable specifications comprise of developing a executable specification, execute the specifications, and then take the customer feedback, and then this iteratively continues. So the specifications is executable, allowing for immediate testing and validation of requirements. So this helps us to have a clear communication between the system requirements and whatever the stakeholders tell. So once the specifications are clear, we this is like simply talking, like every week you meet the customer and then you talk with him, and then you have a conversation with him. So yesterday in the last meeting you told this changes had to be done. We did the changes. Can we move further? If the user says no, inno other change ಮಾಡಬೇಕು ಅಂತ ಹೇಳಿದ್ರೆ, then after next week when we meet him again, we'll again tell, okay, last week you told these changes, we did those changes, can we move further? So by doing this, we can minimize the misunderstandings, and we can work with a clear format, and this is an iterative process. It keeps on happening, right? So this was about the alternative life cycle models. So make sure you write, make sure you draw the diagram properly, and then write 4 to 5 points as explanation for each of the model, okay, each of the life cycle. Moving on further, we have the SATM. So the SATM system, we have seen this in the first module, right? So simple automatic teller machine. It has display screen. It has 3 buttons in which B1, B2, B3 are there. It has a digital keyboard. Digital keyboard numbers are there, and along with cancel button is also there. Then we have a slot for the receipt to come up, and ATM cards to put the ATM cards. And there's a door for depositing and cash withdrawals. And then there are 15 screens in total. We have discussed what are the 15 screens in first module itself. Moving on further, we have the context diagram for SATM system. So context diagram is, it speaks of what are the actions happening to the SATM system and what are the key factors, or what is the context affecting the activities. Okay, so speaking of the terminal keys, so when we consider the terminal keys, with a keystroke we can access the system. So after the keystroke, when I enter my pin, I'll be able to access the system, right? After that, terminal screen. So the terminal screen, when I enter the keystroke, I will get some input, right? That input is displayed to the terminal screen. After displaying it to the terminal screen, here I have the terminal slot. So in this slot, the slot status is depicted, and then the slot command is taken. So here, after entering the key, now I'll enter the pin, right? So the expected PAN is entered into the central bank, that is the system, right? And expected pin is generated back to the simple ATM system. Now we have the terminal door here. So terminal door receives a command from the system, from the SATM system, and depending on that command, the status is reflected back to the SATM system, from where it will be further reflected back to the terminal screen. So the context diagram is pretty easy, guys. I would suggest you to just remember this diagram, and page tumsodu, I hope you can do it very well. Moving on further, we have the level 1 diagram, the data flow diagram. So in level 1 data flow diagram, there are device sense and control. This is 1.1. okay, so device sense and control, in this we have the slot command, slot status, door status, and door command. So slot status and door command would be received from the terminal slots, right? Whereas coming to slot status and door status, it will be like given from the terminal, slot command and door command would be the commands given from the device sense and control to the terminal. It is going from this side to the terminal. Whereas speaking of slot status and door status, the terminal status would be updated to the device sense and control. It is this side. Okay. Next we have the bank. So from the bank, the expected pin is given, and then the PAN is given as the response. Okay. Then coming to the terminal screen and the control here. So terminal sense and control, sorry. So here the screen is, so whatever the output is there, it is being reflected to the terminal, and from the terminal, whatever button we press would be taken here. So we have discussed what 1.1, 1.1, 1.3 speaks of. Now from here, we should look into managing the sessions. That is, whatever keystrokes that I enter would come to 1.3, and from here it will go to managing the session. After managing the session, our output would be generated that will get back to the terminal sense and control, and from here it will get back to the screen. Next, expected pin. So when expected pin is entered, we get the account details back to the central bank communication. Then coming to this part. So here we enter the device status. So if the device is out of service, that will be updated here, and depending on that, the device commands are also reflected back. So level 1 diagram is also easy, guys. Make sure you know how to draw the diagram, what are the functionalities to write here, and you can explain it in your own words. Okay. Next, moving on further, we have the ER model of SATM system. ER model is entity relationship model. So it depicts what is the relationship between the different entities here, the different builds here, blocks here. So firstly, we have the customer. So firstly, we have the terminal. So terminal depicts the ATM ID, status, and what is the cash on hand. So if you look at the terminal and customer, so each customer uses one terminal. So here we have 1:1 relation. So in customer, we have the customer ID and PAN. This was between these two, 1:1 relationship. And between customer and account, each customer will have one account through which he can access the SATM system, right? I'm speaking in terms of SATM system only. So here again, it will be 1:1 relation. One customer has one account. Speaking of this side, transaction and session. So one customer can handle one session, or each session could be handled by one customer, or no sessions could be handled by a customer also. Then coming to this side, we have each transactions would be reflected on each terminal. So whatever transaction is happening would be displayed onto the terminal. That is 1:1 relation is established here. So this was about the ER model. Again, if they ask, this is pretty simple. Draw the diagram and explain everything. Okay. Moving on further, we have the decomposition tree for, okay, before this we have our upper level SATM finite machine. Upper level SATM finite machine might look complex, but then no, it is pretty easy. So firstly, our system is in the ideal state, and then it awaits when we enter the card. If the card is valid, card is okay, then it awaits for the PIN to be entered. So when I enter the PIN, when the PIN is valid, then I move into the transaction section. So in transaction section, I'll select which transaction, be it balance, deposit, or withdraw. And after this, I perform the transaction, and then I come to close session. Now this close session, if I don't want to close the session, I can get back to this part, that is await transaction. If not, if the session is closed, everything is, my transaction is ended, I get back to this idle state. That is, everything is done. Next here, awaiting the transaction, I entered the PIN, I put the card, and if the card is not working properly, then I get back to idle state only. Okay, that's it. So this was about the upper level SATM finite machine, about entering the card and writing the PIN, and then selecting which transaction to take place. This was about upper level SATM finite machine. We have PIN entry finite state machine also, but then that is slightly trickier, so you can leave that part also. Coming to decomposition tree for SATM system. So here, this is a proper structured definition of how SATM system works. So we have made use of decomposition tree here. So the root node here is the SATM system. So from SATM system, we have device sense control, and then central bank communication, terminal sense and control, and managing the sessions. So in device sense and control, we further have door sense and control and slot sense and control. So device sense and control speaks of the door, it could be the cash withdrawal or the deposit door they are speaking here of, and it goes same with the slot also, the slot to enter your ATM, or the slot to enter your card, or the slot to get the receipts. So these come under the device sense and control. Speaking of the central bank communication has no further we cannot deduce it further. There is a communication happening with the bank when a transaction is initiated by the customer. Coming to the terminal sense and control. In terminal sense and control, we have the key sensors and we have the screen driver. So depending on these two, the terminal would work further. Coming to managing sessions, firstly, we have to validate the card. Once the card is validated, we validate the PIN. That is, I enter the PIN. So in entering the PIN, I get the digits, the PIN values, right? After getting the PIN values, if it is valid, I move further, that is to manage this transaction. After managing the transaction, I close the transaction. So looking at the theory part here, a structured chart may miss the fact that some lower level functions are used at many places. That is, a screen driver function is used by many modules but appears only in functional decomposition. To overcome this, we make use of call graph. So call graph is more effective for identifying integration test cases. So to create a call graph, a number decomposition and detailed view of components is required. So looking at how this is done, here we have the functional decomposition outline. So looking at the functional decomposition I outlined, so whatever the diagram we had here, similarly we are writing in this format. Okay, so SATM system would be the heading, device sense and control would be 1.1. Now in this I have 1.1.1, that is door sense and control. 1.1.1 is door sense and control. In this also I can get the door status, control the door, dispense the card. So this is the sub operations which are being performed in 1.1.1. Looking into 1.1.2, that is slot sense and control. In slot sense and control, I can watch the slot card, I can get the card, deposit card status, control card roller, control envelope roller, or read the card script. So these are sub operations which are being performed at slot sense and control. This goes the same for central bank communication. In central bank communication, pin is taken as input, that is first 1.2.1 pin is taken, and then 1.2.2, that is PAN is expected, right? PAN is expected, or 1.2.3 could be like necessary details are given back to the system. Then we have terminal sense and control. In terminal sense and control, we have the screen drivers. Screen drivers input could be taken, or various operations could be done. And coming to the key sensors, when buttons are pressed, I take the values in, and the pin is validated. Then coming to managing the sessions ಅಲ್ಲಿ 4 points ಇದೆ, ಇದನ್ನ expand ಮಾಡಿ ಬರಿಬೇಕು. So this was about the functional decomposition outline. So moving on further, we have, as we spoke of the call graph, no? So we can make use of this functional decomposition. Here I've written everything, okay, right from the SATM system to the process withdrawal. So make sure if they ask an exam, then we have to write this, okay. So moving on further, we have separating integration and system testing. So it is important to separate integration and system testing in order to provide clear distinction, helps avoid testing gaps and redundancies, clarifies goals for each testing level, aids to identify the test case at different levels. Then the discussion is facilitated by threads. So we come across topics called as threads here. So it is a construct that refers to execution time behavior. So when we test a system, test cases are used to select the threads. So moving on further, system threads describe system level behavior. Integration threads describe the integration level behavior, and unit threads describe the unit level behavior. Speaking of the structural insights, so integration testing ali focus on interfaces between the units, assuming individual units have been tested. So in integration testing, as we have discussed in the starting, we first test the unit separately, and after testing the unit separately, we perform integration testing. Coming to system testing, the same system testing definition, guys. Then we have SATM system example for the structural insights. So in this, system testing should see all screens are guaranteed, that is all 15 screens are guaranteed. Then system level threads are, firstly it is invalid card isolation. So these threads are different components, okay, different constructs which are being used. So whenever a test case comes, these threads are activated. So system level threads ali invalid card insertion, valid card insertion with 3 failed pin inputs, then valid card, correct pin, balance enquiry or ಕೇಳ್ಬೋದು, or deposit ಬಗ್ಗೆ ಕೇಳ್ಬೋದು, or deposit ಮಾಡ್ಬೇಕಂತ ಹೇಳ್ಬೋದು, or withdrawal money from the system, or it could be attempt to withdraw more money than what is present in your balance. So this was about the structural insights. Looking at the behavioral insights, we have the system's port boundary include input and output visible to the customer. That is, here it could be the keypad, screen, or the card slot. System test cases are defined by sequences of port input and output events, as they are the primitives of system test case. So behavioral inputs ali what operation you are selecting speaks of how the transaction would occur further. So this was about the structural and behavioral insights for separating the integration and system testing. So this was about the first chapter. Moving on to the second chapter, we have is the integration testing. In integration testing, the first thing we come across is SATM functional decomposition tree. So in order to design this SATM functional decomposition tree, we have to make use of these values. Okay, so here the unit, here the level number, and the unit name is specified. So right from 1 to 27, and along with that there are alphabets also, A, B, C, D, E, F, till F it is there. So I would suggest you to go through the notes once properly, and when you keep this, and when you look at the table, when you look at the graph decomposition tree, it'll be easy for you to understand. Moving on further, we have decomposition based integration. Guys, from this chapter, this question is a must. Okay, 10 marks, it will be asked for sure, so make sure you cover this definitely. So there are 4 strategies. Each strategy describes the order in which units are being integrated. So the function decomposition tree is basis for integration testing because its main representation usually depicted from final source code showing the structural relationship of system with respect to units. So for making use of decomposition based integration, we rely upon the integration testing. That is, we look into how the structural relationship with the units is there, how it is established. So the first topic we have here is the top-down integration. Top-down integration begins with the main program, that is root of the tree. From the root of the tree, the integration starts. Lower level units are called by the program are represented as stubs. So all these lower level units, they can considered as stubs. Okay. So they are throwaway code that emulates these units. So these are the throwaway codes that will initiate these units. So let's look into how the process happens. So develop stubs for all units called by the root. So from the root till the leaf node, we develop stubs for all the roots, and then we start replacing gradually these stubs with the actual code once the main program logic is verified. So we start from here, all the leaf nodes are considered as stubs. So from top, okay, idrinda E functionality is accepted, this unit is accepted, so this much is done. Then I move to this part. Okay, let's look this way. So firstly, I started from here, I came to this part. This was a stub initially, but then once the units were verified or they were replaced with the actual code from the main program, I convert this to the code. Then from this stub, I went further. These 3 were the stubs, and here again I'll consider these 3 stubs and I'll verify with the actual code. Further, after doing this, we'll look into the further aspect, and then that is how from the starting to the end we iterate. That is how top-down integration is done. Moving on to the bottom-up integration, it is opposite of this. Okay, so integration starts with the leaf nodes. So from here we start integrating it. So stubs are replaced by the driver modules. So here we make use of driver modules. So driver modules emulate units at next level up in the tree. So from these we move further, we move above. That is, we make use of the driver modules here. So the process is, we test bottom level units with specially coded drivers. So we test these bottom level units with specially coded drivers, and then once this code is verified, once it is proper, once it is tested, we move to the above level. And from bottom we start conquering each and every tree, each and every unit by making use of the driver modules, and then we conquer the entire program. So the advantages here is typically requires less throwaway code because we are not making use of stubs here, right? So here we make use of the driver modules, and in speaking of the bottom-up integration, the usage of lesser driver modules is happening here. Speaking of the sandwich is a combination of top-down and bottom-up. So in this, the process is to perform integration on subtrees by combining elements of both approaches. So from top also I'll start combining it, and from bottom also I'll start combining it. So challenge here is, although there is less effort in development of stub and drivers, but then fault isolation becomes more difficult here. There could be instances where or the units which are not tested extensively. At that condition, this sandwich integration fails. Okay, so moving on further, we have the Big Bang integration testing. So in this, it is a combination of all the testings, all the types which we have seen previously. So here all component integrated simultaneously, and entire system is tested as a whole. So no incremental integrations is done here. It is simple to implement and time saving, but then higher risk of failure, delayed testing due to complex debugging. So this was about the Big Bang integration. We have discussed the 4 types of decomposition based testing, right? Next, moving on further, we have call graph based integration. Call graph based integration is again an important question. This could be asked for 10 marks. Okay, so make sure that you study this properly. So because the decomposition tree has limitations in terms of complexity and maintenance of the tree structure, we come up with call graph. We have seen what call graph in the previous topic also. So it is a directed graph representing the calls between the modules and can address the loopholes of decision tree. In call graph, we have 2 types. 2 approaches are used. that is pairwise integration and neighborhood integration. Looking at pairwise integration, so the idea behind pairwise is to eliminate the usage of stub or driver development effort. So we restrict a session to just a pair of units in a call graph. So it involves testing pair of directly connected modules in the call graph. So we eliminate the stub or driver development here. So this approach reduces the need to develop stub and drivers, but focus on direct integration between two modules. We'll look into this, how it is done. Okay. So each edge in the call graph corresponds to a integration test session. For example, in SATM, there are 40 sessions in total for pair integration. Okay, so the advantages here is reduced complexity and less development efforts, because when you're making use of the pair integration, no, you just pair the two adjacent nodes, right? So I can pair these two being the first one, and then I can pair these two being the second one, and I can pair these two being the third one, and I can pair these two being the fourth one. So here I have established 4 sessions. It could go beyond 4 sessions also, but then here it makes easier for solving the for performing the integration testing rather than making use of the stubs or drivers here, device drivers here. Moving on further, we have neighborhood integration. Neighborhood integration is again a very simple topic. So the focus is on testing a module along with its immediate predecessor and successor in the call graph. So if suppose this is the node, a node behind it is a predecessor, and the immediate node after that is a successor. So we perform testing between this module. We consider this entire thing as one module and perform testing here. So the neighborhood could be specified this way. So here reduction in sessions is happening. When compared to the pair integration, we had 40 sessions here, but then here we'll be having 12 sessions. So then in order to calculate the value, nodes minus sync nodes would give the neighbor value. So here advantages is fewer sessions, no stub driver development. It is same again as the pair integration. Looking at an example. So if you look at this example, if we have to perform the neighborhood integration, firstly I'll consider node 2. Okay, so for node 2, what is the predecessor? Predecessor is 1. And what are the successor? Successor is 6. Right. So this is one level of neighborhood, SATM neighborhood. Okay. Then coming to 10, if I select node 10, here predecessor would be 3, and here successor would be 11 and 12. If I come to 4, so for 4, here predecessor would be 1 and successor would be 13, 14 and 15. So this is how you can write for if you have made use of here I've made use of 18 nodes, right? So make sure you write at least for 8 of the nodes. Okay. So it again depends on how many marks and how elaborate you have written for the pair integration. It has to be equal with the neighborhood integration also. But then there's nothing much to exaggerate here. These are pretty simple topics. Okay. Next topic we have, and a slightly trickier topic, that is path-based integration testing. So in path-based integration testing, we come across a topic called as unit execution path. So unit execution path is when a unit runs, it follows a specific path of source statements. So if it calls another unit, control is passed to another path of source statements in called unit is executed. So depending on, see, I started from this path, I started from this node and I'm going to this node and I have to follow this certain path. But then if the control is passed to some other node, then this path has to be altered, right? Depending on the source statements which is given by the user, our path would get altered. So this is about path-based integration testing. Unit execution path. How will we handle the calls? We have two options here. Either to treat the call as an exit from the calling unit and enter into the called unit, or it could be to suppress the call during the unit testing, since control would be eventually returned to the calling unit. Here we have certain definitions. So the first one is source node. Source node andre the node from which we start. I hope you know the definition for source node. Sync node is the end node which we come across. Then we have the module execution path, that is from a start node to a end node. Whatever the statements which I come across are module execution path. Then I have message. Message is a mechanism in programming that allows one unit to transfer the control to the another unit and receive response. So examples here could be the subroutines and the procedural call. So moving on further, we come across path graph. So this topic is is not well defined in any of the notes, be it the VTU code or any of the notes. So I would suggest you to just understand the theory part of it. And if they ask, if they ask for SATM also, if this is asked for 10 marks also, if you write the theory part, you might get 5 marks. No, so to be in a safer side, study this part also. So path graph, it is called as definition is module to module path. So it is a directed graph where nodes represent module execution paths and edges represent the message and returns between the units. So this was the intro part of path graph. So this is useful for describing and visualizing how control flows between different units in a program during integration testing. So here, speaking of the path complexity, we come across cyclomatic complexity. We have seen this formula, right? V of G is equal to E minus N plus 2P. So here P is number of strongly connected regions. So for structured procedural code, P is usually taken as 1. Next, we move further. We have the advantages. So in advantages, first one is the hybrid approach. Hybrid approach means path combines what are the actions happening, what is the input output happening with the structural testing. This path is identified through the path procedure. Then we have the consolidation. Consolidation is to cross-check between the functional and structural testing. Integration between these with the system testing is happening. Then we have the applicability. Applicability is we can directly apply this into our code. Then we have the versatility. Versatility is it works effectively for software developed using the traditional waterfall, or it could be the composition based life cycles. Coming to disadvantages, efforts intensive. It requires a lot of efforts to identify the paths, how it is happening and all. Then stub driver elimination. Previously we have discussed that stub driver elimination is an advantage, but then here it is a disadvantage because it becomes difficult when we are dealing with complex graphs. Okay, so when we are dealing with complex graphs, we have to make use of stub or driver elimination method. So here we come to the end of our 4th module. I have tried covering all the important topics. This notes would be available in the description. Along with that, the PDF would also be available. So make sure that you go through my notes firstly and then refer the PDF again. So guys, I would say that in 4th module, we have standard questions. Let me repeat it again. So the first one we have here is the alternative life cycles. So this is for 10 marks. Followed by that, they could ask for decomposition tree system for the SATM system. This is again a 10 mark topic. Then we have decomposition based testing, 10 marks. Then we have call graph based testing, 10 marks. So make sure that you cover these topics properly, guys, and then look into the other topics also. Stay tuned. I'll be uploading the 5th module pretty soon. And if you have any doubts, do let me know in the comments. Subscribe to my channel. Thank you.